Thank you.
Thank you very much.
Thank you. So it is an awkward moment, but we're going to focus on technical stuff. So we heard in the morning about artificial intelligence. So I want to go deeper into where in this automotive driving chain, in this kind of process chain, where the artificial intelligence hides. And there's more than one approach to do autonomous driving, and I'll describe two of them. One is a more traditional approach, and the other approach is what we are doing. And let's start seeing. So we all understand that there are three main technological divisions or technological pillars that we need to tackle, we need to solve if we would like to have autonomous driving. So the first one is sensing, and we all understand about sensing. We have cameras, we have radars, we have laser scanners, we have high-performance computing. All the data goes into the high-performance computing. There's artificial intelligence. No one really can say exactly what that means, and I'll try to be more detailed about that. Takes all this data and provides an environmental model. Okay? High-precision mapping. We heard today from Edzard about high-precision mapping. This is a necessary and critical condition. Without it, we'll not have autonomous driving. The high-definition mapping provides that foresight, provides redundancy. Without it, we cannot have safe driving. And then the third technological pillar, this is where a lot of artificial intelligence is hiding, is the decisions. The driving decisions, we call the driving policy. It is the negotiation skills that we humans have when we are negotiating driving in complicated scenarios like in urban driving. And we would like robotic cars to have similar attributes, similar negotiation skills, yet drive very safely. Okay, so those are the three pillars. So when we look at sensing, let me show you a clip. This is from our Las Vegas demonstration. We had a car together with Delphi going through a 10-kilometer route hands-free in an urban setting. And this is how things look like from under the hood. You can see that the bounding boxes, the 3D bounding boxes around the cars, on the cars. This green carpet is the free space, the traffic lights, traffic signs, and you see this from 360 degrees around the car. Okay. I'll skip this. Let me show you a bit about mapping. So there is a roadbook, a high-definition map that is being built through crowdsourcing. It's a technology that we have been developing for the past year and a half with contract signed with BMW and Volkswagen, and very soon with additional car makers. So you have a map on the cloud, which is now projected on two panes. On the right-hand side, it's projected onto Google Earth, so you can get a sense of accuracy. On the left-hand side, it is projected onto the image space. So if we run this is part of the Las Vegas route. All these dots are landmarks, and you can see the lanes projected onto Google Earth very, very accurately, and the lanes projected on the image space. So you can see this is an accuracy of centimeters. And this kind of information is part of the mapping. So let's go. I'm not going to talk more about this is another demo in London. This is a demonstration that Nissan showed in London. So you can see that the landmarks are these yellow things, the lane marks. The map data is projected on the image space, and you can see that on Google Earth. So let's go a bit deeper. So the first place where we can find artificial intelligence is in sensing. And then I would like to specify exactly where it is hiding in sensing. When people think about sensing, they think about this level, object detection. There are vehicles, there are pedestrians, traffic signs, traffic lights. These are objects. And the problem here is you receive an image as an input, your output is a bounding box. A bounding box around a vehicle, a bounding box around a pedestrian. Right? This is driving assist. This is where driving assist is today. Right? We need to detect vehicles, pedestrians, and other objects, and actuate accordingly. So this is level one. This is the easiest problem. This problem has been solved. There's no need to talk about this anymore. The next level of the problem is understanding the free space, the path delimiters, where the curbs, the barriers, the guardrails, where one can physically drive, where one cannot physically drive. And here we're talking about the input is still an image, the output is a free-form boundary. And at the edges of the boundary, we want to know what is the semantic meaning. Is this a curb, a lane mark, solid, fragmented? What is the semantic meaning behind it? So this is the next level. Here you need more sophistication of algorithms. The third level is really the killer. The third level is drivable paths. Knowing which path takes us where and what is the semantic meaning associated with the path. These two paths are being merged in 50 meters. This path is going to a highway, in highway exit, and so forth and so forth. Imagine the complication of city driving, understanding the drivable paths. And not always we have lane marks. Right? So here the input is an image, the output is a story. I need to describe what I see. It's not a free-form boundary, it's not a bounding box. And we call this strong perception. This is really still an open problem. Okay? Now, this is where all the artificial intelligence is hiding. The first line is a solved problem. The second line is already in production. For example, the first generation autopilot of Tesla has this technology from Mobileye. The third part is really very, very challenging, and there's a lot of artificial intelligence hiding there. Now, the question is, why we need to solve this problem? So I'll skip this one here. And let's look how sensing is utilized. And what I want to point out is that there are two approaches. I'll call the first approach a map-heavy approach, and the second approach is the map-light approach. And Mobileye is the second approach. So let's look at the approach on the left. The approach on the left is very simple to describe. And it's also quite simple to implement, but it's the wrong approach. So I'll explain why. So the first approach is you use a 3D sensor, like a laser scanner, and you detect vehicles and pedestrians, and they are described in the 3D coordinate system of the car. Okay? And then what you do, you localize the car in an HD map, and there are ways to do this localization. If you have a laser scanner, there is laser data also on the HD map, you do a matching, and you localize yourself. So now all what you need to do, you take the vehicles, the vehicles and pedestrians you detected in step 1 and put them on the high-definition map, because you localized yourself. The high-definition map contains all the lanes. So now you know where the lanes are without even seeing them, because they are in the high-definition map. The vehicles are on the lanes, and now you have a unified view. You have drivable paths from the high-definition map, and you have the objects that you have seen from sensing. So far, I did not describe any need for a camera. And if you recall, the first Google vehicles, they had no cameras. They had only a camera looking for traffic lights. It all was based on a laser scanner. Okay, so this is the approach. Now, if you want to create robustness or enrich, so you'd like to add more sensors, for example, adding camera. Every sensor that you add, you need to lift it to 3D. So if you have now camera data, you need to put that camera data on the 3D coordinate system. The problem is that 2D to 3D is hard. Radar data is also 2D. It's a simple, it's different dimensions, but still 2D. Camera data is 2D. Lifting from 2D to 3D is hard. Okay? Our approach is you use the camera to detect both the vehicles and pedestrians and the drivable paths. And remember, detecting drivable paths is difficult, because the camera is the only sensor in which these two types of data coexist together in one view. The camera sees both texture and shape together. You localize the car in the HD map using camera information. This is our REM technology, the kind of clips that I showed you before. You use this localization into HD map by projecting the HD map onto the image space. We're not projecting the image space to 3D, but doing the opposite, 3D to 2D, because 3D to 2D is easy. 2D to 3D is difficult. Right? Now we use that projection to create a unified view of vehicles and drivable paths in 3D, because the map is described in 3D. Now, when you are looking at adding additional sensors like radars and laser scanners, all what you need to do 3D to 2D, and 3D to 2D is easy. Taking laser data, projecting onto the image is easy. Taking radar data, projecting it onto the image is easy. For example, this is laser data, LiDAR data projected onto an image. This is radar data projected onto an image. So 3D to 2D is easy. So now let's see what are the advantages. And this is what you can see here. On the left-hand side is the image space. On the right-hand side is the top view that you see. And we can get a top view very, very accurate using this idea. So camera plus map will give you all what you need, and then the radars and lidars would be for redundancy. So let's look at what are the advantages and disadvantages. The advantage of the left-hand side is it's very easy to do, rapid prototyping. With 6 months, take a team of 10 talented engineers, and you have a very, very nice demo. And this is what Silicon Valley does. Very, very quickly, you can get a demo on the road. Okay? If you look at the disadvantage, the high-definition maps becomes a single point of failure. Without it, you cannot do anything. The drivable paths and the vehicles, they live in different coordinate systems. So now you are creating errors when you bring them into the same coordinate system. They're not seen by a single sensor. One sensor sees the vehicles, the other sensor is the map. Okay, they're not seen in the same coordinate system. And then the real killer is creating these bloody HD maps is very, very expensive. It's not scalable. Right? And autonomous driving would not lift off the ground if there is not a true economical value to it. If the cost is too high, we'll not see autonomous vehicles. And these high-definition maps, the way they're built today, is very, very expensive. If you look at the right-hand approach, the camera is the only sensor that sees both of them in the same coordinate frame. So you don't have these errors of lifting into two different coordinate systems. The high-definition map creation is done using camera sensing, using crowdsourcing, though the cost is almost zero. And then you can, we call these level 2 plus systems. These are level 2 in terms of the driver is responsible, but you can provide features that feel like level 3, level 4, and you can do that without a ladder. So for example, imagine the Tesla 8-camera system with a front radar. Right? This is something like a level 2 plus. It cannot satisfy the safety requirements. There isn't redundancy. There's no fail operational. The driver still needs to be responsible, but you can get a very strong performance, a good feeling of performance, and you don't need a ladder for it. So this opens up business possibilities. Right? And the disadvantage, it is very, very difficult. As I said, the third part of the sensing, that's where a lot of artificial intelligence is required. So the right-hand side is difficult to implement, but in the long run, this is the right approach. The left-hand side is easy to implement, but in the long run, it's not scalable. Again, if we don't build a business, we will not have autonomous driving. Okay? So let me go to the second part where artificial intelligence is hiding. And the second part is the driving policy, the negotiation in complicated traffic. So what I put here is a quote of half a year ago. It's a quote about Google vehicles, but it has nothing to do really with Google. Google is a very good company. It's all autonomous vehicles that we see out there suffer from the same problem, is that their driving policy is too simplistic. Whenever something complicated happens, the test driver needs to take control. They cannot negotiate the kinds of negotiation that we humans can do. And the point on the left is that driving is a multi-agent game. And the other agents are humans. The other agents are not robotic vehicles. They don't cooperate like computers. They're humans. They are aggressive. They make mistakes and so forth, and we need to cope with them when we're doing robotic driving. And at the same time, we need to guarantee safety. So just to give you an idea of how things look in the real life, I took a drone and took some clips of my way to work. Okay? Now, it is in Israel, so it's more aggressive than here in Germany, but there are places that are even more aggressive than Israel. So let's have a look at this. Okay, so what we see here, that the kind of squeezing in that driving does. So this car, for example, that is now in the circle, would not succeed in merging. So it's not that our negotiations always succeed. And we're fast-forwarding it, and still the car is not succeeding. We're fast-forwarding it, and the poor guy, nobody lets him get in. Right? So this is real life, right? And the one here, the long truck, is going to work quite hard. And now we're fast-forwarding as well, because it's taking a long time. So imagine kind of the planning that needs to be done here, right? So If you are thinking that there's an autonomous car out there that can do something like this, then you are completely fantasizing. And it's not even close, not even close, okay? So let me go to something more concrete. And this is the double lane merge, right? This is a project that we're doing with BMW, right? Solving now a very specific problem that is a very difficult problem, right? So this is called the double lane merge. So if I run this, double lane merge is where you have vehicles from two sides merging, where vehicles on one side can go right and vehicles on the other side can go left, or they can stay in their same lane. Now, why is this challenging? Because this is not just squeezing in. You may interfere with the plan of the other car and create deadlocks. And there are no rules. The only rule is simply don't make accidents. Right? People not normally say that the four-way stop is the most complicated negotiation. Actually, it's not the most complicated negotiation because there are rules. There are rules of right-of-way. You simply need to comply with the rule of right-of-way and squeeze in. Here, there are no rules, so it becomes difficult. Okay? And you need to plan many seconds ahead. So the search space, if you are kind of opening the tree of all possibilities, it grows exponentially with the amount of time that you need to plan ahead and with the number of agents. So it's really a computational, very, very difficult problem. And we would like to do it like humans. Okay? So why is this challenging? Let me first show you real life. Again, this is on my way to work. So this is a double merge. What you see there on the left-hand side is a double merge. So have a look at it a bit, and now we'll see how things can get complicated. So here's the first thing, that the car in the circle, is really obstructing traffic while he's doing his merge. And what you're going to see now is not very rare. These two cars, a deadlock, okay? And it's not very rare. It happens, okay? And we need to cope with these kinds of situations. Right? Okay? Well, we don't have audio, so we don't know what happened there between these two guys, right? Okay. So what is the complication here? When we want to solve these very, very complicated tasks, the tendency is to use machine learning. It's data-driven. Now, what is the advantage of machine learning is that it's much easier to observe and collect data than understand the underlying principles. In many situations, in text-to-voice, in natural language processing, in computer vision, history shows that understanding the underlying principles is difficult, but collecting data and using machine learning as kind of a data-driven approach provides much better performance. So the tendency is to go to machine learning, and it's the right tendency. What is the disadvantage of machine learning is the performance is based on the statistics of the data that you're using for training. And it means that you're going to have corner cases. And finding those corner cases requires lots and lots of data and many, many trials until you sift out all the corner cases. So why am I telling you all of this? Because what you are normally used to think about is supervised learning. And this is what's going on with sensing. So with sensing, you are sensing the present. And the technology behind sensing the present is what you heard before, is deep supervised learning. You have a network, image in, label out. Okay? But when you're thinking about driving policy, you're planning for the future. Planning for the future is a different machine learning technology, which is called reinforcement learning, in which you are interacting with the environment. Now, why is that different in the pragmatic way? It is different because the way we use data. In supervised learning, the actions or our predictions do not affect the environment. They have no effect on the environment. Therefore, we can collect all the data in advance. We can collect all the data offline, and then use the data that we collected offline to train our networks again and again and again and again until we sift out all the corner cases. In reinforcement learning, our actions affect the environment. That means if I decide to turn left, I'm affecting the other cars. So now if I change my software, then I need to collect all the data again. You cannot collect the data in advance, because every time I change my driving policy, I'm changing the way I affect the environment. I have to collect all the data again and again and again. Now, this is a problem, because I mentioned corner cases. Now, corner cases in this case is accidents. Accident is a rare event. Now, sifting out those cases that are rare requires a lot of data. Now, every time I change my software, I need to collect all the data again. It becomes a problem. This is why the classical way of dealing with path planning does not involve machine learning, because the proposition here is not attractive. It's not that you can collect your data once, right? So we found a way. We found a way to somehow solve this problem in a way that we can use machine learning, guarantee safety, without creating this explosion of data. We published it. You can find it in my website, in our website. And let me show you here some simulations. Again, you have the red cars need to go right, and the white cars need to go left. And and in each trial, these 8 cars are placed randomly on the stretch. And you can see that there are quite complicated maneuvers going on here. Okay. Since we're reaching the end of this. And if you look at the statistics, in this case, there were about 100,000 runs. In each run, there are 8 agents placed randomly. 0% accidents, because the way the model is built, and I urge you to go and read the paper, the way the model is built, it is guaranteed that there's not going to be any accidents. And now we measure the success. Only 200 out of the 100,000 trials did not succeed. And when you look at these 200 trials, you really see that even a human would find it very, very difficult to succeed with those trials. It means the car would be placed close to the end of the stretch, and there's no time to do the maneuver or something like that. When you look at the computing time of this kind of algorithm is very attractive. So let's say in a 10 frames per second system, 10 hertz per second, this policy takes 1% of the sensing computing, 1%. So if we have our IQ chip that is handling sensing, this kind of algorithm takes only 1% of it. Okay? And this is because of the machine learning. In the classical case, you are opening a tree of all possibilities, and it explodes exponentially. When you're using machine learning, it's like playing the AlphaGo, the Google game that they won the game of Go. You're opening a tree, and you have a clever way of traversing this tree using data-driven methods. The same thing is happening here. Okay? So imagine this as the automotive version of AlphaGo. Okay, if you'd like. So here is another last example of kind of squeezing in, and this will be my last slide. Okay, and here all the agents are being trained to act like humans, and you can see that this is kind of a complicated maneuver of squeezing in maneuver, and it's working quite well. Okay? So if I'm summarizing what we have here in terms of where artificial intelligence is embedded. So first, if you want to do sensing right, there's this element of strong perception, of understanding the drivable paths, that the traditional methods are avoiding it. They're relying too much on these LiDAR-based high-definition maps in order to avoid this complicated part. But if you don't do this complicated part, you don't have a scalable system. Second, mapping done right, you use a strong perception to automate the high-definition map building and using crowdsourcing. So then our entire concept of this, the REM technology that we have been working on, is to be able to automate completely the high-definition map building using the strong perception. Okay? Third, the driving policy done right, you need to reach human-level negotiation. You need to be nimble as human, yet guarantee safety. Okay? And this is a great challenge. We are just beginning. You can look at the paper that we wrote. We have a strong collaboration with BMW on that aspect. And this is really an element, if we don't solve it right, we will not see autonomous cars. So to do autonomous cars, we need also to solve this part, the driving policy. It's not only the sensing and the mapping, it is negotiating into traffic. And there's a lot of artificial intelligence. Okay? Thank you.